Okay. Good evening, everybody. I hope everyone's having a wonderful day. So just before I get started, I just want to give you a quick reminder that assignment 4 is out. It is that programming assignment. It has you doing some stuff with hashing and a bit with sorting, for example, and all sorts of fun stuff. I did put out the discussion video the other day, and you have everything to be working and completing it. So there's nothing to wait on. You can feel free to just work on it as you will. And it's due about the middle of next week. So just keep an eye out for so just look for the dates on the assignment on your courses. Anyway, sorry, I'm just getting very excited here because we're going to be moving into what I would consider kind of like the final big chapter of this course. So we talked about all sorts of different data structures in this class, and we've been working up to a bunch of different ADTs, for example. We've talked about things like dictionaries, we talked about stacks, we talked about queues. I'm going to be talking about, in the last part of this class, and this is going to be kind of a big component of the class, are trees. Now, at first, when you hear that, you're like, okay, what are we going to go look out the window or something? No, we're not doing that. These are different kinds of trees. So what is a tree? It is just simply an abstract model of a hierarchical structure. So for those that aren't familiar with the idea of a hierarchy, you have different levels in a hierarchy. So you can think of different things such as a file system. You might think of the directories on your computer, for example, where you have different folders all at different levels in the file system. Likewise, you can think of it like a company. So for example, here's a company I call the Computing Co. Always lovely and fun. It has different divisions, sales, manufacturing, and research. Now, its sales division has two components, has a Canada one and an international one. And it seems to have for its international one, Candyland, the United Kingdom, and the United States. So listen, if I could get under the Candyland division, that would be pretty epic. But the point is that I have different levels. If, for example, I can think of this as a hierarchy, and there's different organization to it. And the big thing is that there's a parent-child-like relationship the hierarchy has. Likewise, I have manufacturing here. I can have my one division for laptops, and I have another one for desktops. But the point here is that you can model all sorts of things with trees. And these kind of structures occur all over the place. So I want to talk about what it means to talk about a tree. That means I'm going to have to talk about some terminology that trees have. So just keep that in mind, as there's going to be a whole bunch of terminology I'm going to lay on you. We're going to have a bit of fun with this to try to figure out what each of these things mean, okay? So you might think of a tree like something a little complex like this is an organization, for example. These can get quite complicated. Many trees can. Now, in computer science, we really like drawing trees, not like this. Don't think of it like a tree that's going up like this. Think of it instead of as a tree that's pointing downwards. Usually the convention is we have the tree being drawn downwards from what we call the root. So we're going to be interested in things called rooted trees. So we call it that because these so-called trees have a special designated entity, which we refer to as a node, akin to what we talked about with linked lists, for example. We have the so-called root node that's designated. So we call whatever this is the root. Just like Computing Co. here, this is the overall organization very top. That we'll designate that the root. So that's where all of it seems to come from. So I got to talk about some terminology. So there's a lovely picture. And as I said, nodes have what we're going to refer to as a parent-child relationship. So we're going to have a root node. There's going to be other nodes. And these nodes are connected by edges. And the idea is that if ever I have a node, it's potentially able to have children. Likewise, each one of the nodes may have a parent. But I want to point out that there's one node that always never has a parent. It's the root node. So just keep that in mind. So I want to talk about some of the terminology I'm using here. So these things I draw as lines, sometimes people draw these as directed arrows. the mother node. I like that. I like that. You could think of, so each one of these nodes is connected by an edge to a potential child. And the idea is that this, as I said, dictates a parent-child relationship. So, for example, I would call A the root node. And if I want to talk about parents, so if I look at sometimes we call these vertices as well. So this is usually in more broader context, but for us, I'll mostly refer to them as nodes. So these nodes here, if I look at node with this B in it, well, B is a parent of E and F. So notice that I have E and F here. The way I draw it is that it goes from the root, which is the ancestor of all of the nodes, downwards towards its descendants. So if I have E and F, that means if I look directly above, they both come from a common parent, B. But that's one way. For example, again, I could always say, okay, well, what's the parent of say, C? Well, it's A, right? It's the one that's directly above it if you follow its edge upwards. So we call these lines edges. Sometimes we call them links. Sometimes we call them arcs, depending on the context. I'll usually refer to them as edges or links in this context. So I'll ask you one more. So for example, if I wanted to talk about what is the parent of J, can somebody tell me what the parent of J is? So the parent of J is F. Yeah, so just look at the one that's directly, it precedes, because it's a parent-child relationship. So if I have this node here, if it comes directly below like this and it follows downwards, that means that these are the children of F. So we have different terminology for these things. So for example, we have this concept of a sibling as well. So for example, if I wanted to consider node C, so this node that has a C in it, well, its siblings are B and D. Why? Because they have a common parent. Could somebody tell me what is which nodes are the siblings of J? So if I look at J, which ones are the siblings? I and K, very good. So far we got an idea that we think about it like a hierarchy where I have it where they have a parent-child relationship. So for example, if I look at this node, this is its parent. If I look at this node, its parent is B. And if I look at this node, its parent is A. Likewise, just the other way reciprocally, if I look at this node, its children are these three nodes, and so on. So there's a notion of children and a parent. There's also a notion of ancestors and descendants. So ancestors just simply meaning those that came before as their parent, their grandparent, their great-grandparent, and so on. And descendants as in, oh, this node's child, the grandchild, the great-grandchild. So let's talk about some more of this terminology. So do we have any questions about so far root, parent, and sibling? Are we doing okay so far? Give me 2 thumbs up if we're okay with this so far. Because I've got a bunch of terms I want to lay on you. And we're going to have some fun doing this. So, let's go this way. So, I already talked about children. So, the children of a given node. I'm going to lay some more terminology on you. And we're going to have some fun with this, okay? So, anyways, so like I said, I talked about children, I talked about ancestors and descendants. So I'm going to keep this tree right here so that can help us walk through this. So I talked about children. So for example, I already told you that the children of A are B, C, and D. And likewise the descendants. So notice that the descendants, these are all of the nodes that are going to come as children, their great-grandchildren, and so on. So for example, if I look at B, all of its descendants are its children, and all of those children's children, and so on, all the way down. So in our case, I have E, F, I, J, K. Likewise, the ancestor, like I said, it's just each one of the parental figures as we go up. So for example, if I'm at I, its parent is F, then its parent is B, and its parent is A. This means that if I looked at I here, its ancestors are F, B, and A. Likewise, I can do the same exercise with J. But remember, this is something rather important for you to keep in mind. I want you, if you're writing this down, put some asterisks around this. That A has no ancestors in this example because it is what? What kind of node is it? What did we designate it as? It's the root. The root never has an ancestor. So keep that in mind. It sometimes plays as an important condition in a lot of the algorithms we're going to explore later. So just keep that in mind. So now we're going to go through some more terminology, but I thought we'd have some fun with this where we'd have some fun kind of figuring them out. So we have to first talk about an internal node. So an internal node is simply a node with at least one child. So for example, let's talk a little bit about this. Can somebody tell me what are all of the internal nodes of this tree? So you know right away that any node that has at least one child is an internal node. So for example, you know right away something like A is an internal node, right? So could somebody tell me what all of them are? So let's see. We got B, C, F, and A. Yeah, there should be 4 of them. Yeah, that's them all. That's all of them. Wonderful, wonderful. So for example, I'm just going to list them in alphabetical order. A, B, C, F. Okay, how about, let's talk about leaf nodes. Sometimes they're called external nodes. I'll usually refer to them as leaves or leaf nodes. So which nodes are the leaf nodes? So these are ones with no children. No children. I must stress that there's more of them. There are more of them than the internal nodes in this case. So I see a whole bunch of different listings here. I'll tell you up front that there's about 7 of them. Let's see, we got 1. So we know E definitely has no children, right? I has no children, J has no children, K has no children, G most certainly has no children, right? H doesn't, nor does D, right? So these are all leaf nodes, right? So those are all leaf nodes. So let me list them out. I'm going to list them in the funnest order I could think of. If that's even a fun word to say. E, I, J, K, G, H, and D. I just went around the tree, around the bottom like that. I just kind of just did a swing, a little tour around. I just kind of, that's how I listed them over there. So next, we got to talk about the depth or level of a node. So all this is just the number of ancestors. So if I look at node E here, how many what's its depth? Can somebody tell me what its depth is of node E? Very good. It's 2. Very good. Very good. Its depth 2. So far we're doing okay. It seems not too bad. It's just learning some new terminology for trees. So remember, the reason why its depth is true is, it's 2. I was about to say true. Its depth is 2. It's because notice that I follow through all my ancestors. Well, its ancestor, I have 1 ancestor, then 2 ancestors. That's how I got 2. Very good, everybody. So now we got to talk about the height of a tree. Now, this is a very important concept for us. So this idea of the height of the tree. So the height of the tree is the maximum depth of any node in the tree. So if I look at this tree, can somebody give me an idea of what the height is? Any ideas? Any ideas? What is the height of this tree? Let's see, we got some ideas here. Some are saying 4. Well, let's think about it. Remember, it's about the number of ancestors, the maximum number of them. It's the max number of ancestors. So let's see. So you know right away it's probably going to be one of these nodes we would want to consider, right? So I'm already seeing what I'm looking for, but let's see. We got 1, 2, 3, and that seems to be the largest I can get for number of ancestors. So in this case, the height of the tree is 3. So I will tell you up front that if ever I want to know the number of levels as opposed to the level of a node, some have answered 4. That's actually what it would be if I want to know how many levels there are. Very commonly, people index the levels starting at 0. They go like 0, 1, 2, 3, and they can ask, oh, how many levels are there in the tree? They'll say, okay, well, there's 4 levels. Just it starts off at a depth of, or a level of 0, namely at the root here. So that's just one of those things that's helpful to keep in the back of your mind, is that always the number of levels in total in the tree at most is 1 plus the height of the tree. But that's just a side note. So note that we have other kinds of terminology I want you to be aware of. For example, one that's going to be relevant for us today is the concept of a subtree. So here's the idea. It's really not that complicated at first. It sounds a little complicated at first, but so remember, when we count the ancestors, the whole idea is I start at my node and I count the ancestors, right? I don't count myself because I'm not my own parent, right? Because if I'm at the root, for example, I have no ancestors. I am the root. I am the root. So this notion of a subtree is very simple. So it's just simply going to be the tree that consists of a node and its descendants. So what I can do is if I give you a tree that looks like this, what a subtree would be in this example is, say, for example, I wanted to have the subtree that's rooted at C. All it is this node and all of its descendants. So a subtree of C here would just simply be this tree, and that's referred to as a subtree because it's contained within this larger tree. Likewise, you can think of the tree itself as a subtree of A, for example. Or you can think of, if I had it where the subtree, when I consider the node with B in it, well, all of this, that's a subtree rooted at node B. So very often we'll use this idea when we talk about the root of a subtree, when we think about trees recursively. This is going to be a very powerful tool for us when we're developing algorithms, is that a tree, when you think about it in terms of a subtree, you can always describe trees in terms of themselves using this definition. Does anybody see what I mean about this? So for example, if I were to pick my root, well, true, it's a subtree of itself by just simply saying, oh, it's a subtree of the tree that has it where this node is the root, right? Likewise, if I pick C, well, this is a subtree, but notice it's a tree too, right? So this is in fact a tree, this is a tree. It's always within the context of whatever I decide is the root. So just keep this in mind and keep it actually in the back of your mind. We're going to use this idea today. So 2 other things I wanted to point out is that we have this notion of an ordered tree. So this simply means that the children of the nodes are ordered. So sometimes we'll give a special meaning to the children and the order they come in. So for example, when we start talking about what we call binary trees, I'm going to often designate there's going to be in those cases 2 children. I'll very often want to have a left child and a right child. Can a subtree just have a single node? Correct, it can. So for example, I could just simply say, okay, I'm going to give you the subtree at J, and it's just itself. That's it. And of course, an unordered tree, that's just where I'm not going to impose any ordering on the children. So for example, you'll notice that I've kind of labeled these nodes kind of like this. You'll find that it's rather helpful for me to do this, so it's for visualization purposes. But say if it actually meant a very special ordering for us. So for example, if I were to switch J, G, and H, perhaps I'm trying to maintain that as I read them level by level, I want to make sure that they maintain an alphabetical order, for example. That may be one thing I may be interested in. If I swap these two, they're not in order anymore. So that's an example of an unordered tree. But the point is it's not imposing any ordering on the nodes, in particular their children, the relationships they have with the parents. So one thing I want to point out is that we can define an ADT around these definitions. So if you want to compute, for example, the parent, you want to compute the children, if you want to determine the number of ancestors, aka if I want to determine the depth of a node, I can determine and actually define an ADT around all of these terms. So I'm gonna let you take a look at that in the notes. I feel like it's not really something beyond just these terms, just recast as functions. So I want to start really just having a little bit of fun with this. So why don't we get into this and have some fun? So the first thing I want to do is show you how you can represent a tree like this in a computer. That's probably the first thing that I might have to show you. So I'm going to draw a picture, and I assure you, at first it'll look really complicated, but it's actually not. So I'm going to show you one way you can implement a tree. So the first thing I need to point out is that this is a very general tree structure. We're going to see as we progress through the course, more specialized versions of these. So if you look at this and you're like, oh man, that looks really complicated. Dan, why are you showing us this? It's because I want to show you a broader way of representing a rooted tree on a computer. Then I want to show you ways that you can specialize it beyond that. And when I specialize it, it makes the structure a lot simpler to work with. So just keep in mind that. So one standard way you can represent a tree like this, a rooted tree, just a general rooted tree, is using what we call the linked tree representation. So this is one standard way of doing it. And I'm going to draw a rather sophisticated looking picture of the following tree. So I'm going to erase this tree here. And instead I'm going to draw a simpler tree just to make things a little easier for us to see what's going on. Because I got to make sure I show you this at least once. So you know how when we have linked lists, for example, a linked list that has a data attribute and has a next attribute, right? Well, we're just going to take this idea and we're going to extend it. So instead of just having it where it's just one next attribute, we're going to have many next attributes. And those next attributes are going to be our children. So I'm going to draw out a tree here, and I'm going to draw the corresponding one represented as this so-called linked tree. So first I'm going to show you what the tree, what I'm thinking about looks like if I were to just draw it out at a higher level. So in this case, I'm going to have the root be C, and its children are A, F, and D, and the children of F are B and E. So I'm going to show you how I'm going to represent that tree over there. So here we go. So I'm going to first show you what one of these nodes looks like, and then we'll proceed from there. So first, I'm going to have some variable that's going to be pointing at one of these nodes. So you can think of this like the head of a linked list, for example. It's actually just like it. We just call it the root as opposed to head. So just keep in mind that. So I'm going to have three attributes here. So I'm going to first have one for my data. So I'm going to have a one for my data. I'm going to have another attribute for my parent. The parent is going to be a pointer or reference to the parent node. So just like when we talked about parent and children, the parent and child relationship, I want to represent that in this generalized tree. As we go further, we're going to see that we can actually specialize this, and it's a lot less complicated looking. And then the last attribute is going to be the children. I'm sorry, I'm running out of space a little bit here. But the third attribute are the children, which is going to be a pointer to a collection that's going to contain pointers to nodes that are its children. So usually for our purposes in this class, we'll just think of it like an array. But I must stress that you can take any one of the data structures we talked about, like a list, a vector, any of those kinds of collections, you can always put them in for what we're talking about here when I draw it in a moment. So first for my data, suppose that it's a pointer to some object C, for example. So this is our data attribute. Remember, the root has no parent, so I'm just going to write null or nil. That's what I just mean the same thing. And then I'm going to have a pointer to some collection. And in here, I have 3 children, right? So it's some collection. So I'm just going to indicate that this is some collection. You can think of it like an array. So you can just think of it as an array if it keeps things simpler. But like I said, you could easily swap it out for other data structures if you like. So now I need to finish drawing out all these other nodes so we can start playing the game of connect the dots, I guess. So let me just draw out the rest of these nodes. So I'm going to need one for A. I'm going to need one for F, and I need another one for D. I need another one for B down here. And I'm going to need another one for E. I'm giving myself some space here, so just keep that in mind when you're doing this. So I'm going to put A here. I'm going to have F, D, B, and E. So those are all the data attributes for each one of the nodes. And now I'm going to play the game of connecting all of the parents. So remember, the second attribute I have here is the parent. So when you're implementing this as a class, all you're going to have as your instance variables, you're going to have a data attribute, you're going to have a parent attribute, then you're going to have these children. Like I said, you can think of it like just like an array. Or say, for example, if you have a fixed number of children, very often you can think of them as designated variables, as we're going to see when we start talking about so-called binary trees. So let me draw in the parents. So we know that A's parent is the root here, which is C. The parent of F is this node 2. And the parent of that node is also the one that contains C. Likewise, the parent of B's node is F. And the parent of E's node is F. So far, we're doing okay. I've just filled in the parent attributes so far. Are we doing okay so far? Any questions so far? I still have to put the children in. So remember, each one of these nodes is going to have its own collection like this one. I haven't drawn them in quite yet. So just think of it like a node when we had a linked list. So instead of it just being data next, now I'm going to have one that tells me the parent node as organized like this. And I'm going to have another attribute that's going to contain pointers to or references to the children. So you can think of it like I just took the linked list node and I jacked it up on steroids. Like now it's a big buffed node. By the way, don't take too many. Please don't jack yourself up like that. I'm just being playful here. But that's I will leave it at that. I'm just having a little bit of fun with you guys. So anyways, let's continue here then if we're doing okay. So, you know right away that A, D, E, B, and E here all are leaf nodes. You know that they don't have any children. So, I don't really store anything here. I can put nil here. It could be just an empty collection, for example. It doesn't matter too much. It depends on how you're storing these collections. If it's just an array, you might just create the array when you have a child, for example. Or it might be a linked list, for example. In fact, linked list might be a pretty good one to pick. Who knows? Depends on what kind of data structure we need. An array is sufficient. So, let's talk about these children. So we know F has 2 children, right? So I'm going to create the collection that contains the children for these two. Well, the first one is B, the second one is E. And I know up here I have 3 children, right? I have these 3 nodes as my children. So this would be a way I could represent this tree. Sorry, I just got very excited there. Hopefully that wasn't too loud. So this is how I could represent this tree in the most general form possible for what we need for any rooted tree. As I said, we're going to specialize this structure as we go along. So I just want you to be aware of a way I could represent this tree. Are there any questions? So just think of it just like a linked list, how we had a node. Just like we had a node there. I'm just saying the node now has 3 attributes. It's data. You can think of this like next, except now it's pointing to its parents, each one of them. And these are truly like the next references or next pointers. Just it's a collection of them. So are we okay with this so far? Because I want to start talking about some fun properties of trees. Okay, great. But yeah, don't worry, you will get some fun exposure with this on the final assignment, but we'll be looking at a much more specialized version of this one, okay? So I'm not expecting you to just whip this out of nowhere. Just to be very clear. But as long as you understand the idea of how it's just an extension of what we would do with a linked list, it's just got more stuff. So now I want to talk about some properties, and then we're going to start talking about some algorithms, so what we can do with trees. Because trees, like I said, they're very nice in the sense that they model all sorts of stuff. And they're also rather effective as data structures for all sorts of ADTs, like dictionaries. So the first thing I wanted to talk about is a property of trees that I want you to be aware of. So I'm going to give you an interesting theorem. So I'm going to let M be the number of edges and N be the number of nodes. And here's a theorem. Here's a theorem. Is that the number of edges is always 1 less than the number of vertices or nodes. So this is a nice thing about trees. And the proof is really simple. It's so simple, I'm just going to show you with this picture. I have a proof in the notes, but I want to just show you how I can easily derive this. And it's by counting. So for those that like counting, I'm going to show you how I can count the edges in relation to the number of nodes. In fact, let me do a different color. Let's go blue. Here's a blue. So what I want to do is I'm going to try to pair each one of my nodes with an edge. I'm going to try to find a clever way of doing this. So let me look at this tree, for example. And I must stress, just pointing at an example is not an example of a proof. In fact, that's not what a proof is. But I'm saying is the argument I'm going to present works for any old tree. Any tree this works. So here we go. So here's a very natural way I can derive this for you. And the proof goes like this. So all I'm going to do is I'm going to pair each one of the nodes here with the edge that links it to its parent. So I'm going to pair each one of these nodes with the edge that makes it reach its parent, the one that connects it to its parent. But notice here, and I like to think of it like suckers, for example. So imagine this is like a sucker. Like I could pull it off and I can lick it. So the question is, okay, so I was able to pair each one of the nodes here with an edge. Except there's one node that we know does not have a parent, right? which node has no parent? There's one node. It's the root. The root has no parent. So if you count up the number of edges I've paired, look at it. Each one of these pairs up with every node except for the root. And if there's n nodes in the tree, that means I've paired every edge with every node except for the root, which makes it so it's one less than the number of nodes that are in the tree. Hence this result. So this is a nice bound to be aware of. It's a relationship that the edges and the nodes have in the tree. This is always true with trees. I must stress that this result is true for even if I don't have a designated node as the root either. So it's a very broad result about trees. In fact, many will tell you, yeah, this is actually one of the key parts of how we define a tree. That's how vital it is to what a tree is. So, where are we going with this? I thought we would start looking at some things we could do with trees. So, the first thing I thought we would try doing is try to compute the height of a tree. So you recall we talked about the height of a tree. Remember, that's the maximum depth of a node. And remember, the depth is the number of ancestors of that node. And I want to find the one with the largest depth. And whichever one has the largest number of ancestors, whatever that quantity is, that's the height. So let's talk about computing the height of a tree. So this is the first algorithm I'm going to show you what we could do with a tree. So let's suppose I want to compute the height of a tree. So this is the first problem we're going to consider on a tree. And I must stress that this algorithm, you can easily specialize it for any kind of tree data structure. That's why I'm giving it in this very general form. So recall the height of a tree is the maximum depth of any node, right? So I'm going to draw out a tree, and we're going to try to figure out what's going on with it. I'm not going to so much worry about what I'm using to label the nodes. I'm just going to draw some nodes out. One thing I do want to point out is typically when we draw trees out, we try to line them up by level. It makes it easier for us to read it. It makes it you don't have to draw it like that, but it makes it very easy to read. That's just a point of advice. So suppose that I have the root, and I'm going to call it the root R here. And I want to compute the height of this tree. Can somebody tell me what the height of this tree is, by the way? What's the height of this tree? Yeah, it's 3. Very good. Very good. So you know right away that the height is 3. But you might ask, Dan, how can I actually come up with an algorithm that does that? So remember how I told you of this idea of a subtree? Does anybody remember that? Is that if I pick any one node, I could define a subtree on that node and all of its descendants. So for example, if I pick this node, all of this is a part of its subtree. And I could think of that node being rooted at the one I designated. So we're going to try using this idea to come up with a recursive algorithm for computing the height. And I will tell you up front, there's actually going to be a recursive definition of how I can compute the height. So we're going to use our friend recursion to achieve this. And you're going to see that recursion is a very useful way of talking about trees and how we can compute things on trees. So that's the first thing I'm really going to try to convince you of. So the first thing I want to think about, let me just get a different color out. Please don't mind me, I'm just kind of wiggling around here. So if I look at each one of these nodes, the leaves. If I look at the leaf nodes, what are the heights of each of these? The ones I just circled in blue. What are the heights of each one of these? So if I were to take this as a subtree, what's its height? I'm not talking about the whole tree here. I'm talking about if you imagine this is the root of the tree. So it's 0. It's 0. So remember, I'm looking at the subtrees here. So all of these have height 0. Now you might ask, Dan, where are you going with this? That seems kind of interesting. What are we doing with this? Well, I want you to think about this. We're going to try to figure out a relationship so that we can compute the height based on parts of the tree so that, one, I don't have to do anything too sophisticated. I just pass my work on to the subtrees to do all the hard work for me. That's one thing that makes recursion rather elegant. So imagine I considered this subtree rooted at this node. What is the height of this tree? The one I've just outlined in green. It's 1. It's 1. So this one, it's 1. Likewise, if I were to pick off this one, its height is 1, right? But here's the thing. You might ask, okay, so how do I know that as a matter of fact? Well, you know that because you know the entire tree. But here's another way of thinking about it. Well, you know that if I looked at this one node and I imagined it was rooted at some subtree, I know its height is 0, but most certainly when I go up to its parent, I have to have gone and I've examined one parent, right? That means that there's one extra ancestor I've just introduced. So regardless of which of these two I pick, I'm going to introduce a new ancestor. That means that the height will go up by 1. So notice here that it didn't really matter which one I picked when I thought about the height being 0 of each of these subtrees, but that may not be true. So let's consider another one. So for example, this subtree, the one that's rooted at this node, this one's height is of course 0. But let's look at this one directly to its right, this bigger one. Can somebody tell me what is the height of this tree? Where that's the root. It's 2, right? It's 2. So here's a very simple way of thinking about that. Okay, so how do I figure that out? Well, look, one of my children, if I take that as a subtree, its height is 0. This one's subtree, its height is 1. Well, I can take the larger of these two and add 1, right? Because when I go up to its parent, whichever of these two I pick, probably the larger of the two, right? In terms of height, I just always know I'm going to add 1 because I go up the tree, right? So naturally, when I ask, what's the height of this whole tree? Well, look at it. I have a 1 for the height of this node, if I think of it like a subtree. So if I look at this whole tree here, and if I look at this whole tree here, its height is 0, and I look at this whole tree, its height is 2. So which of these should I pick? So I'm just going to label them with a letter here to make it easier for you guys to type it. So if I have A, B, and C, which one is the one I should be picking to add 1 to? A, B, or C? Yeah, I'm seeing the C's. Seeing the wide C's. I'm seeing the wide C's. Yes, exactly. So you know that this is the tallest of the subtrees, right? So I know I'm going to take this one's height, and I add 1 to it, and that's how I find out that the height is 3, right? So do you see an interesting thing going on here? That I can completely determine the height of the tree based on computing heights of my subtrees based on my children. Or if I take each of my children as a root of a subtree, I can compute the height of those and work my way down the tree, and I can figure out that when it hit a leaf node. Does anybody see that? Isn't that interesting? So I can define the height in terms of my heights of my children. Is that kind of wild? So that brings me to talking about how I can write this recursively. So you see how I could do it like this, right? So I just pick the larger of these values and I add 1 to it, right? That's what I did every single time when I did this. So here's a way I could define this. So I could say it's the height. So suppose I want to compute the height of r, where r is the root. Now you can imagine when I take this and apply it recursively, I can imagine if this was the root, this was the root, this is a root at some point in this. But let me write this out for us. So we know that the height of a subtree rooted at a leaf node is 0, right? So we know it's 0 if r is a leaf. Otherwise, we know it's an internal node. So I'm going to take the max over all of the children of r. So I'm going to use a max function, but I'm going to do it over each one of the children. You're going to see how this looks when I write out the pseudocode. At this stage, it looks quite like a really good mayonnaise and mustard sandwich, okay? But I assure you, it's very easy to think about. So this is if r is internal. So it's just the maximum among all of the children of my node. I look at its height, and then I just add 1. So I take the larger of them, just like I did over here. So this is a recursive way of writing it. This is the recurrence relation for the height of the tree. So if you ever wanted to write this out as a formula, here you go. So naturally, you want me to write it out as an algorithm, right? So why don't we do that, okay, everybody? So let's head over here. Let's go over here. And let's write this out as some pseudocode, okay? So you're going to see that all I'm going to do is translate this into a recursive algorithm. Now, one thing I do want to point out with the linked tree implementation, depending on what the underlying data structure is, if you want to go through the children, you can imagine it like I'm indexing through the children. If it's an array, it's literally indexing through the array. But you may have seen this idea of an iterator, and we briefly talked about it in class. But if you had a general container, for example, like a list, for example, you could use an iterator to go through each one of the children, and you can map this into something called some people refer to as a for each loop. But in C++, we could write this out in several different ways. But I'm just going to write it as what we call a for each loop. So this might be indexing through an array. It might be using an iterator, like you may have seen when you've seen in the lab, maybe the list, the standard library list, for example. You could do things like that with the list. It's really neat. So anyways, let's write out an algorithm for this. All I'm going to do is translate what I wrote over there. So let's write out the algorithm. And I must stress that this is going to be a recursive algorithm. So I'm going to call it height r. Its input is going to be a root r of a tree. And the output is going to be height of a tree. So we're going to have two cases. Remember, we like to identify a base case and a recursive case. So I'm going to start off with the base case. So we know what the base case is when r is a leaf, right? So if r is a leaf, so I must stress that if you ever want to find out if r has a leaf, you could just simply, in your implementation of the nodes, you can have this actually as an attribute in each one of the nodes. Or you could have for your collection, you could gather what its size is. For example, if the collection is like a list, you could just access its size function. So if you wanted to find out if it's a leaf, it most certainly has nothing there, right? It's either going to be null or it's some collection and it has no elements in it. So this is something you could easily determine in constant time, assuming that you organize the implementation appropriately. So if r is a leaf, then I'm just going to return 0. That's what my formula over there says, the one we came up with together. Yeah, I'm calling dibs on it, okay? So anyways, let's proceed. So now, if it isn't the case, it's an internal node. And remember, all I want to do is figure out what the maximum number is of the heights of all my children. So think about it. We have a way of doing this, and we've talked about this idea before, the idea of sequential search. So for example, I could scan from left to right through the collection, and I could just simply figure out which one has the largest height, right? Just like if I was computing the largest number in an array. So I could just do the same idea. So one thing I want to point out is that the height never is negative. So there's some conventions where the height is defined for certain nodes as -1, but for our purposes, it works perfectly fine to be where I'm going to use -1 as a value that is always going to get beaten by one of the children that I'm going to access at some point. But I remember, at this point, the whole idea is I'm going to have this kicking around so that if I had no children, I'm going to add 1 to it, so that if I was, say, a leaf node, if I have no children, it's going to add 1 to this and it'll make it 0. So I just want to consider if I do have some children, I better see if I have any. So I'm going to use a for each loop. This is just going to go through each one of the children pointers. If there's any, for each child C of R, we're going to do the following. So I'm going to compute the height of my child. So I'm going to call recursively height on my child C. And then I'm going to just simply do no different than if we did a sequential search through the array. If you think of it like an array, imagine I go through each one, I compute the height. I want to keep track of the one that's the largest number, right? It's no different than solving that problem that you've seen in the past. Just now there's just this tree structure that's going on. So all I have to do is I just simply check if h is greater than max height. Because that means that I found something bigger if this is satisfied. I found a larger height. So if this is satisfied, then I better update max height to be h. Because I found a larger quantity for the height. And that's the end of the for each loop. And I'm just going to simply return. Because remember, in our definition there, I compute the largest of the heights, then I add 1 to it. So I return max height plus 1. And that's it. So this is the elegance of recursion. See, look, you thought at first it would be something a little bit more daunting, but it actually isn't. It's really just got 2 problems really bedded inside of it. Computing the largest number in a collection. So to compute that number, I recursively apply height. And I just simply get the largest one out of them by maintaining a variable that if I run into a better number, I'm just going to update my number. So this is a recursive way of writing the same thing I wrote over there as that formula. So let's talk about an analysis here. So now let's analyze the running time of this algorithm. So I must stress, as always, I do have a written description of the analysis. For the sake of time, I'm going to walk us through how I'm going to derive a complexity function. So let's do this. So I'm going to identify the number of operations that are going to happen. So when I deal with a recursive algorithm, what's the first thing I do? So do you remember what I did before? What's the first thing I did? Yes, exactly. You consider the non-recursive work first, right? So we're going to ignore this recursive call. We're just going to pretend that it's just some constant number of operations for now, and then we'll incorporate it back in afterwards, okay? So, oh yes, thank you. There's a curly brace I missed right here. Thank you. Yeah, there we go. So, let's walk through this. So, the first line, checking if R is a leaf. Well, this is some constant number of operations, right? I'm going to call that C1. C1 is a constant. So some constant number of operations. Now, notice that I have this first line here, and then I have this work that's going on outside the for each loop. What I'm going to do is I'm going to take these 2 lines, I'm going to kind of lump them together into C2. So these will take some constant number of operations, right? Then, if I'm ignoring the recursion, because remember, I'm going to first ignore the recursion, so ignore the recursion. How many operations are happening in here? So some constant number, right? Now you'll notice, first thing I need to point out is that if we think of worst case analysis here, it's just notice that the behavior of this doesn't really branch at all, right? The only thing is just updating this one variable here. So regardless of what the tree looks like, I'm still going to compute height, right, on each one of the children. So you'll notice that the worst case analysis isn't going to be interesting to really consider as like something very special. In this case, it's just going to execute the same way regardless. So I want to make sure I mention that, because usually when I do worst case analysis, I identify some worst case scenario. Here, notice that there is no branching behavior other than when I hit a leaf versus what isn't a leaf, right? An internal node. I still do these recursive calls regardless. So, now the natural question is, what's going on here? Well, I have this loop here that goes through the children, right? The children. So, I'm going to have this. So all of this, well, this is going to be the number of iterations of that loop times C3, right? Well, let's think about it. What would number of iterations be? Any ideas what we could think of as the number of iterations here? Yeah, the number of children, exactly, very good. So the first thing I want you to notice is that the number of iterations is the number of children, which I'm going to denote as numchild of R. So this is just simply the number of children of R. I better add that in. There we go. Perfect. So now I'm going to put this all together into a complexity function, then we're going to simplify it, okay? So let's walk over here. In fact, let's kind of take a little bit of a prance. I don't know. I'm just gonna get my daisies out. I'm just gonna start just grabbing some flowers. I'll just start twirling them around. It's a lovely, lovely evening. Let's finish up this analysis here. Okay. Now it's a good time with everybody. No, it's always a pleasure to have fun with everybody. See, the first thing is just having a good time, because if you aren't having a good time, it's hard to learn, right? But we're throwing a lot of concepts at you, so just keep in mind that we're still playing with a lot of different ideas today. So let's talk about the time complexity now. So let's throw this all together in a blender and see what happens. So in the base case, we know we're going to have C1 many operations, right? That's when I get the leaf occurring. So it is indeed going to be a leaf. And I know in the base case, C1 is going to happen, right? So there's C1 operations in the base case. And C2 times C3, sorry, C2 plus C3, man, that would be really not working out well for us. C3 times numchild R. I must stress that I can always add the C1 into here, and it doesn't make any difference at the end of the day, just to be very clear. But let's proceed. So, because remember, all of it could just be collapsed into C2 anyways. It's just some constant number of operations. So this is what happens in the recursive case. In the recursive case. Now, we got to bring back in our friend recursion. Okay, so remember, when I have a tree, say for example, I have a tree that looks like this. I start up the algorithm at the root, right? That's how I would start up the algorithm. Well, if I do a call on the initial one here, well, I do recursive calls on each of its children, right? And then I do a call on this node. Like, keep in mind, this one will finish, that finishes. But this one, I have to call it on those children. So how many recursive calls are happening? Or in fact, how many function calls are happening? Just to be more precise with my language here. So how many are happening? Now, don't think of a cold number. Think of what this would represent. So how many nodes with respect to the input? So in this case, I have nodes and I have edges, right? But in particular, our data structure maintains nodes. So technically, the total number of recursive calls is n minus 1. But remember, I still have to call the function at the beginning from the root, right? So it's really just 1 per node. So observe that the number of calls, and I mean this as in function calls, is 1 per node. So I'm going to put this all together now. So I know how many recursive calls are happening, and I'm going to split it apart based on these operations that are going to happen. So the total number of operations is, now I'm going to explain what I'm going to do with this notation. It saves me a little bit of time when I write it like this, so I'm just going to explain it. So I'm going to sum over all of the leaves in the tree. So each of the leaf nodes, for each leaf node that's in the tree, I'm going to add C1. So for example, if I had this tree, for example, notice I have 1, 2, 3, 4. That means I'm summing over 4 nodes. So if I would do this sum 4 times. So I have C1 plus C1 plus C1 plus C1 for each leaf node in the tree. Because those are all my base cases, right? When I hit a leaf node. Then I have the recursive case. So for each internal node of the tree, and I'm going to give it a name. I'll call each one of the internal nodes as I sum through them all. I'm going to call it U. So for each one of those, we know that it's C2 plus C3 times numchild of U, where U is the internal node. So for example, if I was at this node, say if that was U, you know right away it's going to be C2 plus C3 times 2, right? So I'm just going through each one of the internal nodes and I get the number of children because we know that's how many times the recursive call is going to happen. So let's put it all together now. Well, I'm just going to use some symbols to make this a little easier for me to express. Then we're going to pull out some fun properties. So I'm going to have C1 times the number of leaves. So I'm just going to write it as number of leaves like this. That represents the number of leaf nodes. Plus C2 times the number of internal nodes. Plus, and I'm just going to distribute this sum here. So now I'm going to have all the internal nodes summed up. So I do it this many times. Now I have the C3 times numchild U. But notice U depends on this sum here. So we can't just simply do something very simple with it yet. So I'm going to end up with plus C3 times the sum over all of the children for all of the internal nodes. So I have this so far. Now, something interesting came up in the chat that I want to address that we're going to use. Okay, so when I want to sum over the number of children for each internal node, so for example, this node here, well, that's these children, right? When I consider this node, this is an internal node, I consider those children, right? So I have a question for you. How many children actually are there from the perspective of an internal node? So we're not counting the leaf nodes, we're counting the internal nodes. From the perspective of an internal node, how many of them are, generally speaking, with respect to the tree itself? I'll start writing and then we'll see if anybody has any ideas. So we have some ideas there, but let's see. Well, the sum of the number of children for all the internal nodes is, well, think of it. If I'm at each one of these internal nodes, well, each of its children has a link that connects me from myself to my children, right? That's true for every one of the internal nodes. So we have a name for for that number. So for the number for all the internal nodes is just the number of edges, m. And using the tree property I showed you earlier, so I'm just like losing it here. We know that m is equal to n minus 1, which that came up in the chat earlier. So now I have a relationship between the number of children and now the number of nodes in the tree. So now I can simplify this down. So the number of operations is the following. It is equal to C1 times the number of leaves plus C2 times the number of internal nodes plus C3 times n minus 1, which, if you think about it, can there be more leaves than nodes in the tree? Can there be more leaves than nodes in the tree? Yes or no? No, right? Because leaf nodes are nodes. Likewise, we could say the same thing about the internal nodes, right? So it means that all of these numbers, number of leaves, number of internal, they're all less than or equal to n, right? So that means this is less than or equal to C1 plus C2 plus C3 times n. This is big O of n. So it means that this algorithm runs in big O of n, where n is the number of nodes in the tree. So this is quite nice. It's linear in the number of nodes in the tree. So I want to spend my last bit of time here today talking about how we can explore a tree. So I'm going to talk about tree traversals just for a little bit, and then we'll wrap things up from there, okay? So let's head over here. Camera, come on with me. Come on with me. Here we go. So let's head back over here. I want to talk about tree traversals, okay? Because once I finish talking about tree traversals, I'm going to give you one example to read in the notes of how you can apply one of these tree traversals. And then when we come back next time, you can see, we can start talking about binary search trees and binary trees, which those we're going to have a lot of fun with. So let's talk about tree traversals. So one natural thing that we would like to do with our trees is be able to explore all the nodes in the tree. So just like when I have a linked list, I like to be able to traverse through the linked list. I need to have some way of being able to do this with a tree. Now, depending on the structure of the tree, I might be able to impose special orderings that allow me to specialize how I can do this. But for much more general trees, we only have so many kind of options to play around with. But I'm just going to give you a couple of examples of how we can do it. A tree traversal visits the nodes of a tree in a systematic manner. In a systematic manner. So there's two types of traversals I would like to introduce to you here. So there's two of them. There's one is called post-order traversal. And the other one's called pre-order traversal. So the first one, now you might ask, Dan, how do I exactly explore a tree? So you can actually pick up the same techniques we used just a moment ago to simply say, hey, look, I could examine all my children, and then I could look through each one, and I could go my way downwards through the tree by examining them recursively. So the question is how we're going to achieve doing this. So we have post-order traversal, and we're going to have pre-order traversal. These are going to dictate whether I visit myself and do an operation at myself before my children or after my children. So you're going to see that the framework of this is going to be very simple. So here's a post-order traversal is. It's just simply a node is visited after its descendants. So suppose you want to visit all your descendants before yourself. So for example, you're summing over all your descendants so you could store some number within your node, for example. That's one way you could use post-order traversal. Pre-order traversal. So a pre-order traversal is simply the same thing. A node is visited before its descendants. So I'm going to write out a skeleton for what one of these would look like. So it's really straightforward. So, interestingly, somebody's asking, is this depth first versus breadth first? Well, I wouldn't usually prescribe those words here, but there is a relationship with these two types of traversals with things such as those. So I usually use those terms for talking about general graphs, which is something I talk about in 340. But I want to keep it simple here. So here's the simple framework for doing this. So suppose I'm going to do pre-order first. So suppose I give you a node V. I'm going to visit myself first. So this could be some function. For example, you're getting some number from your node for some calculation. That's what visit is. It's just some generic function. You can put whatever you like there. It's something that's being done to V. Then you just simply go for each child C of V. You do pre-order of C, and that's it. So you can generalize this, you could specialize it even further. Quick question, what can I do to make post-order? Any ideas? What's post-order? What would post-order look like? Based on what I've defined post-order to be. Where should visit go? Where does visit go? Does it go before the loop, like I have here in pre-order, or does it go after the loop? Yes, exactly. So if you want to know how to write post-order, you just simply write the same thing. So you just have algorithm, post-order, with a V. It's the same thing, except you're just going to swap, you're going to move this below the for each loop. And that's post-order. So it's just simply that modification I made over there. If you want to copy that down, feel free to my guest. I have it in the notes. But I must stress that I'm going to give you an example of a post-order traversal application in the notes. I'm going to ask you to read it. So I'll give you an application. C notes for the post-order traversal. So I'm going to ask you to take a look at that. I have an algorithm in there, and we have another analysis. So if you really didn't get the ideas what we're doing here today, there's another example there you can walk through, and also shows you how you can compute the space complexity for the algorithm too. So remember, in a space complexity, we also have to take in mind that the call stack can introduce recursive calls, each one with their own set of data. So sometimes if we do many recursive calls, that adds up a lot of extra memory. So just keep that in mind when you're reading that part. So that being said, I'm going to stop right here. When we come back next time, we're going to start talking about binary trees and binary search trees, which are going to be like the bread and potatoes of what we're going to talk about for the remainder of this term, except we're going to be generalizing further and further up until we deal with some really sophisticated data structures that are sort of the backbone of many types of modern systems, such as databases. So the goal is I'm going to get you up to data structures that look almost like those ones. So that being said, we're going to stop right here, and I'll see you another day. So have yourself a beautiful day. I'll see you later.